Piling is a fundamental technique in construction used to transfer loads from structures to deeper, more stable soil layers. When building structures, particularly high-rise buildings, conventional shallow foundations, such as isolated footings, strip footings, and raft foundations, often fail to provide adequate support. This is where pile foundations come into play. Pile foundations are broadly classified into displacement piles and replacement piles. Displacement piling involves hammering precast piles into the ground, which creates high noise and vibration levels, making it less desirable in urban areas. Due to these disadvantages, construction companies now prefer replacement piling, a quieter and more efficient technique. This method involves removing soil and replacing it with cast in-situ concrete piles. Filling bentonite involves pouring bentonite slurry into the drilled borehole to stabilize the excavation. It prevents soil collapse by exerting hydrostatic pressure on the walls, suspends cuttings, and is later filtered to remove sand impurities. The marsh cone test is used to measure the viscosity of bentonite slurry, which affects its flow and suspension properties. In this test, a marsh funnel is filled with 1,000 milliliters of bentonite slurry while blocking the bottom outlet with a finger. The time taken for the slurry to flow through the funnel and fill a measuring cup up to 1,000 milliliters is recorded. The standard viscosity range for bentonite is 30 to 90 seconds, ensuring optimal performance in piling. The mud balance test measures the density of bentonite slurry, ensuring it provides adequate support for boreholes. The mud balance cup is filled with bentonite, leveled and sealed with a lid. The arm is balanced by adjusting the counterweight until the bubble aligns at the center. The recorded density, typically 1.12 to 1.25 grams per milliliter, ensures proper borehole stability and prevents soil collapse. The sand content test determines the percentage of sand in bentonite slurry. The slurry is poured into a sand content apparatus mixed with water and filtered through a mesh. The retained sand is measured to ensure minimal abrasiveness in drilling operations. Area preparation involves clearing and leveling the site before piling begins. It includes removing debris, marking pile locations, setting up guide frames, and ensuring proper drainage. This step ensures accurate alignment and safe working conditions. Equipment installation involves setting up machinery required for piling. It includes positioning the drilling rig, BG machine securely, ensuring stability on-site. Guide frames are installed to maintain pile alignment. Casing pipes are placed for borehole support, and bentonite circulation systems are set up for drilling fluid management. Additional equipment like tremie pipes, cranes, and concrete pumps are positioned for reinforcement cage installation and concreting, ensuring efficient and precise pile construction. Cutting out the surface opening is a crucial step in piling to ensure proper pile installation. The process begins with marking the pile locations according to the design layout. Excavation is then carried out to remove topsoil and weak surface layers, creating a stable base for drilling. A temporary guide casing is often installed at the surface to maintain alignment and prevent soil collapse. If working on a reinforced concrete surface, a concrete cutter is used to create precise openings. The exposed area is cleaned of debris and leveled to ensure accurate drilling. This step ensures pile stability and proper load transfer to deeper soil layers. Gauges installation is essential for monitoring pile behavior during load testing. Dial gauges are fixed to measure settlement and deflection. Strain gauges are attached to reinforcement cages to monitor stress distribution. Accelerometers and load cells are installed for dynamic load testing. Proper gauge placement ensures accurate data collection, helping assess pile integrity, bearing capacity, and overall structural performance. Diaphragm wall construction is an advanced technique used in the pre-construction stages of deep excavations for subterranean structures, such as basements, foundations, and retaining walls in mega high-rise buildings. This method, widely adopted in international construction projects, has recently been implemented in Sri Lanka by Access Engineering plc, notably in the ITC Tower project in Colombo. The process ensures structural stability, cost efficiency, and environmental sustainability. The first step in the diaphragm wall construction process is the guide wall construction. The guide wall marks the boundaries within which the excavation will take place. It helps maintain accuracy and alignment for the trenching process. A concrete platform is created at the horizontal ground level to ensure stability for the excavation equipment. Excavation of the diaphragm wall is carried out using a powerful grabber machine, such as the GB34, which ensures precision in vertical trenching. The machine's onboard computer system controls the tension, minimizing lateral oscillation and maintaining vertical alignment. This step is crucial to ensuring that the trench remains structurally sound during the construction phase. Bentonite feed plays a crucial role in diaphragm wall construction, primarily in stabilizing the trench and preventing soil collapse during excavation. Bentonite slurry, a mixture of bentonite clay and water, is introduced into the trench immediately after excavation to maintain the integrity of the soil and prevent caving in. This process is essential for deep excavations, especially in unstable or waterlogged soil conditions. The bentonite slurry is prepared by mixing bentonite powder with water in a controlled process to achieve the right viscosity and density. The slurry is then stored in silos before being pumped into the trench. These silos ensure a continuous supply of slurry, which is crucial for maintaining excavation progress. As the grabber machine excavates the trench, bentonite slurry is continuously fed into it. This creates a hydrostatic pressure against the trench walls, counteracting soil pressure and preventing inward collapse. The slurry remains in the trench until the concrete pouring stage. During concreting, the bentonite slurry is displaced to the surface and pumped back into silos for desanding and reuse. During the concrete placement process, self-compacting concrete, SCC, is poured into the trench through tremie pipes. As the trench fills, bentonite slurry and any detritus, including sand and other particulates, are displaced to the surface. This ensures that only high-quality concrete remains in the wall structure. However, the upper portion of the freshly poured concrete often contains weaker material, which needs to be removed. To address this, a head-cutting process is performed. Workers hack away the unsound head concrete until they reach the solid, structurally sound portion of the wall. After this step, a T-beam is installed to reinforce the top section of the diaphragm wall, completing its structural integrity. The final step in diaphragm wall construction involves soil anchoring, which enhances long-term stability and verticality. A clem machine, known for its flexibility in confined spaces, drills holes along the diaphragm wall's perimeter. Reinforcing bars, soil nails, are inserted into these holes and secured using high-pressure cement grouting. Wedge plates are then added to secure the nail ends, ensuring reinforcement and load distribution. This anchoring technique is also effective for slope stabilization and retaining structures. Throughout the process, inclinometers monitor vertical and lateral movement, ensuring the wall remains within strict tolerances. The successful completion of large-diameter shaft drilling projects requires a combination of global expertise and deep local knowledge. At the Grosvenor mine in Queensland, Australia, a significant drilling operation was undertaken to construct a 7.8-meter diameter shaft using advanced drilling techniques and specialized equipment. This project demonstrates the seamless integration of cutting-edge engineering solutions with on-ground experience to ensure precision, safety, and efficiency. The initial phase of the project involved the construction of a secant pile wall to provide structural stability and groundwater control. A 1,200 mm diameter hard, soft secant pile wall was drilled using a BG-28 drilling rig. This technique ensures interlocking piles that enhance structural integrity and mitigate soil movement during subsequent excavation and drilling phases. The secant pile wall plays a crucial role in supporting the shaft and preventing collapse, making it an essential component of the project. Following the completion of the secant pile wall, a reinforced bearing slab was constructed to serve as a stable foundation for further excavation and drilling activities. This slab supports the heavy drilling equipment and provides a level base for operations. Additionally, a pre-sink operation was conducted, removing the initial layers of material to facilitate deeper drilling and shaft development. This phase required meticulous planning and execution to ensure a smooth transition into full-scale shaft excavation. The core of the project involved drilling and reaming the 7.8-meter diameter shaft within the confines of the secant pile wall. This was accomplished using a CAH 500 drill mounted on a Liebherr 885 base crane. The CAH 500 drill is renowned for its capability to handle large diameter drilling tasks with precision and efficiency. The Liebherr 885 crane provided a stable and powerful platform, allowing for the controlled lowering and extraction of drilling components throughout the process. The drilling operation consisted of multiple stages, beginning with pilot hole drilling, followed by progressive reaming to achieve the full 7.8-meter diameter. Given the varying geological conditions encountered, the project required a flexible approach to adapt to hard and soft rock formations. Advanced monitoring systems were employed to ensure alignment and accuracy throughout the shaft excavation process. The Lotus Tower, or Colombo Lotus Tower, is a prominent landmark in Colombo, Sri Lanka. Standing at 351.5 meters, 1,153 feet, it is the tallest self-supported structure in South Asia and serves multiple purposes, including telecommunications, observation, and leisure. The tower's design, inspired by the lotus flower, a symbol of purity in Sri Lankan culture, reflects the country's aspirations for development and progress. The concept of the Lotus Tower was introduced to enhance Sri Lanka's telecommunications infrastructure and to create a significant tourist attraction. Initially proposed to be built in Peliyagoda, the project was later relocated to the waterfront of Barra Lake in central Colombo to maximize its visibility and accessibility. The tower's lotus-inspired design symbolizes purity and the nation's flourishing development, aligning with Sri Lankan cultural values. On January 3, 2012, the Telecommunications Regulatory Commission of Sri Lanka, TRCSL, entered into a contract with two Chinese firms, China National Electronics Import and Export Corporation, CEIEC, and Aerospace Long March International Trade Co., Limited, ALIT. The project's estimated cost was approximately $113 million, with funding primarily secured through a loan from the Exim Bank of China. Construction officially began on January 20, 2012, marked by a foundation stone-laying ceremony. The site, strategically located on the Barra Lake waterfront along Dr. Wijewardene Mawatha, was chosen to enhance Colombo's skyline and serve as a central hub for telecommunications and tourism. The Lotus Tower's architecture draws inspiration from the lotus flower, a symbol of purity in Sri Lankan culture, representing the country's progress and development. The tower's base resembles a lotus throne, formed by two inverted trapezoids, and its color can change through RGB lighting. Covering a floor area of 30,600 square meters, the 350-meter-tall structure is designed to accommodate various functions. Telecommunications. The tower supports digital terrestrial television broadcasting, ISDBT, telecommunications and observation facilities. It is equipped to handle 50 television services, 35 FM radio stations, and 20 telecommunication service providers. Tourism and leisure. The tower includes an observation deck, restaurants, a hotel, and a ballroom, aiming to boost tourism by offering panoramic views of Colombo. Commercial spaces. The podium houses a telecommunications museum, exhibition halls, conference facilities, supermarkets, and food courts, making it a multifunctional complex. Construction milestones up to September 2014. By December 2014, the Lotus Tower's construction had reached a height of 125 meters. This milestone indicated significant progress in the structural development of the tower. The Lotus Tower project faced challenges, including financial discrepancies. During the opening ceremony in 2019, President Maithripala Sirisena alleged that an advance payment of 2 billion rupees made in 2012 to Elite was unaccounted for, as investigations revealed that the company did not exist at the registered address. The University of Moratuwa provided key consultancy services for the project, involving over 70 Sri Lankan experts and engineers specializing in various fields, such as structural engineering, concrete technology, and electrical engineering. The construction also offered practical training opportunities for engineering students from both public and private universities, contributing to local capacity building in high-rise construction and project management. As of September 2014, the Lotus Tower project had made substantial progress, reaching a height of 125 meters. Despite facing challenges, including financial discrepancies, the project continued to move forward, aiming to become a landmark symbolizing Sri Lanka's development and technological advancement. The involvement of local experts and institutions played a crucial role in the project's progress, ensuring that the tower would not only serve as a telecommunications hub, but also as a center for tourism and commercial activities. Pile driving is a critical phase in bridge construction, ensuring stability and load-bearing capacity for the structure. In the case of Shibushi Road, Bridge Number 2, P3 Pier, this process involves multiple steps, including pile installation, pile head processing, and final completion to ensure the foundation meets structural and safety requirements. The project is part of the Shibushi Road Reconstruction, R312 section, and involves constructing a bridge pier, P3, by driving piles deep into the ground to create a strong foundation. The contractor for this project, Amamizu Corporation, is responsible for executing the pile driving work with precision and adherence to safety and quality standards. Before pile installation begins, engineers conduct site surveys to analyze the soil composition and determine the appropriate pile type and depth. This ensures that the foundation can withstand the bridge's weight and external forces, such as seismic activity and environmental conditions. The pile driving process involves inserting long, cylindrical piles into the ground using heavy machinery such as hydraulic hammers or vibratory drivers. These piles, typically made of reinforced concrete or steel, serve as deep foundation elements that transfer structural loads to deeper, more stable soil layers. Once the piles are driven to the required depth, pile head processing is performed. This involves cutting the upper part of the pile to a specific height and shaping it to create a smooth and level surface for the next construction phase. The pile head is also reinforced and treated to ensure a strong connection with the bridge pier's footing. After pile head processing, engineers conduct thorough inspections to verify the integrity and alignment of the piles. Any necessary adjustments or reinforcements are made before the final completion stage. Once approved, the piles are ready for the next phase of bridge construction, such as placing footings and columns. Pile driving plays a crucial role in ensuring the longevity and stability of the bridge. By transferring the bridge's weight to deep, stable layers of soil or rock, piles prevent issues like settlement, structural instability, or failure due to weak surface soil. The use of advanced pile driving techniques and strict quality control measures enhances the durability and safety of the bridge foundation. Pile head treatment is a crucial process in deep foundation construction, ensuring a secure connection between the pile and the structure above. This procedure is especially important for in-situ cast piles, where the pile is constructed directly at the site. The process begins with the excavation of the pile head to expose the concrete and reinforcement bars. After the pile is cast and cured, the excess concrete at the top is removed to reveal sound concrete that can effectively bond with the pile cap. Various methods, such as chipping with pneumatic tools or hydro-demolition, are used to achieve a clean surface. Once the pile head is exposed and trimmed, the reinforcement bars are prepared for integration with the pile cap. Any damaged bars are repaired or replaced, and the remaining reinforcement is cleaned to ensure proper bonding with the new concrete. In some cases, epoxy coatings or bonding agents are applied to enhance adhesion. The next step involves leveling and ensuring the pile head is at the correct height. Precision is critical to maintaining structural integrity. After final checks, the pile head is ready for the pile cap construction, which distributes loads evenly across multiple piles.